Welcome to the module on El Nino. We will actually be learning a little bit today about El Nino, La Nina, and some of the what we call teleconnections, how El Nino and La Nina affects the atmosphere, which in turn affects the atmospheric waves, which finally affects the type of weather that we see across the globe. To actually understand El Nino, we need to get an idea of ocean currents. And many of you are probably very familiar with the ocean current that moves along the eastern seaboard of the U.S. And you see right here this type of ocean current moving up from warm waters. It's called the Gulf Stream, and moves along the eastern seaboard of the U.S. We also have currents that go from south to north, north to south, and actually notice the rotation of this set of waters. The blue indicating cold ocean currents, the red indicating warm ocean currents. And notice that we have a clockwise flow of this ocean current. What type of pressure system in the atmosphere has winds that are clockwise? Well, high pressure. So if I were to draw on a high pressure system, the winds in the atmosphere around high pressure are clockwise. And it's actually these winds, these pressure systems, that actually generate the movement in part of ocean currents. So if we were to draw one down here in the southern hemisphere, however, we have winds here that are going counterclockwise. Now, this is also a high pressure center. But notice the winds are causing the ocean currents to move counterclockwise. In the southern hemisphere, high pressure systems, the winds from high pressure systems flow counterclockwise. So see, here's the equatorial region. The equator is right here. And so high pressure in the southern hemisphere rotates counterclockwise. Now, what's nice about the ocean currents is that they transfer energy. They transfer warm water from equatorial regions northward to more of the middle latitude regions where we're at, right around 40 degrees north. And so then we take some of the cold water, move it down south. So we're transferring colder water down south, warmer water up to the north. Now, what is the source for this cold and warm water? Well, we'll talk about that in just a little bit, just a few moments. Now, what you're looking at here, it's really interesting. It's an infrared imagery. Okay, so there's a satellite in geosynchronous orbit above the Earth. We learned about that a while back. And it's actually measuring the amount of radiation, you recall that from Chapter 2, given off by the oceans and by the land. And I'm going to outline the east coast of the U.S. Here's Florida, Panama City, Tallahassee, somewhere in that area. So this is the eastern seaboard of the U.S. Now we're up into Canada, and all of this area here is the Atlantic Ocean. Notice that we have some darker red. I'm kind of outlining circulation pattern here of warm water coming up from the Atlantic, moving north and northeast, and we have some of the cooler waters here in blue, but we see this nice flow of warmer waters up into northern latitudes. So we're taking the warm, moist, oceanic flow and moving it further north. So when this warm water moves further north, we're actually redistributing energy. We're taking warm, moist air, because we have air that's moving along with the ocean, and transferring it northward. Well, earlier I talked about, let me just back up here a moment. I mentioned that let me see if I can erase this here a moment. Now, you notice here the blue along the western coast of the U.S., there is cold water moving down from the north. Well, typically the air is cooler up here, and so there is some surface cooling of the oceanic surface. But the source for the cold water along the western U.S. has to do with something we call upwelling, and I'll talk about that here in just a moment. But you're looking at temperatures in degrees Fahrenheit. Let's see, San Francisco is right here, and Mendocino, Cape Mendocino, is up in Northern California, and you see some of the coldest sea surface temperatures occurring right along the coast of California. And as we move further south, the water begins to warm, but it's still pretty chilly. And cooler water up here to the north. Now, obviously this water is in further northern latitudes, and so obviously it's going to be colder. We know as we move poleward, or move toward the pole, temperatures begin to cool. But what is the source of this cold water right around Northern California? In fact, this cold water, it's pretty cold from about the northern border of Oregon down to California. So what's the source? Why all the cold water here? Well, it's something we call upwelling. And we have something, there's actually a lot going on here. Let's look at this particular schematic here. You see California, you see the mountain range indicated here, and you have high pressure sitting out in the Pacific Ocean, and we know that winds around high pressure are clockwise. And so these winds moving along the ocean surface begins to actually take surface water and move it away from the coast. And so as we remove the surface water, now we'll look at this particular area, we're taking surface water and we're moving it away from the coast. We're removing water. But you don't see a huge dry hole right along the coast. If you go out to California, you see water. Well, if you take some of this warmer surface water and move it away from the coast, then you begin to replace it with cooler water from the subsurface. And so now the subsurface water moves up and now becomes cold surface water. You see the temperatures down here, 52 Fahrenheit, 54, cooler water below surface. And so what's really interesting is this high pressure with the winds begins to move surface water away from the coast. And so as we move surface water away from the coast, we replace it with upwelling, water moving from subsurface up to the surface, and the temperatures of this subsurface water is quite a bit cooler. So the high pressure system is actually helping to produce these cold areas of water. Well, you're probably wondering, what does this have to do with El Nino? I haven't mentioned El Nino, I haven't defined it yet, but I'm giving you some background on ocean currents and temperature profiles of oceanic surface. Now the question comes up at this point, where exactly are we looking at the occurrence of El Nino? Where does El Nino actually occur? Well, let me go back here a little bit to a earlier map that I have here. Typically El Nino occurs right here, right around the equatorial region, down here right around Peru. That's right near where Peru is located. And so when we're talking about El Nino conditions, or La Nina, we're talking about this region from South America over to Australia. So we're talking about the impact of water temperatures and atmospheric pressure patterns. When we're talking about El Nino, we're talking about two items: sea surface temperatures and atmospheric pressure patterns. In fact, you'll hear El Nino referred to as the El Nino Southern Oscillation, ENSO. If I go back here to my title page, notice I have ENSO, LENSO. This is El Nino Southern Oscillation, La Nina Southern Oscillation. When I'm talking about oscillation, I'm talking about how things change, and specifically pressure patterns. So El Nino Southern Oscillation has something to do with atmospheric pressure patterns changing along with a change in sea surface temperatures. So keep in mind, as we talk about El Nino Southern Oscillation, we're talking the equatorial region, right around 0 degrees latitude, and we're talking about the area from Peru off the South American coast all the way over to about Darwin, Australia. So we're looking at these waters here. Okay, let's learn a little bit about water and sea surface temperatures and pressure patterns during a normal type situation. Now keep in mind, here's Peru, Ecuador, here is the equator. So again, we're very familiar where we're at here. And typically in non-El Nino conditions, in normal conditions, we're looking at depth of water here. And from here to here is about 50 meters. So this is about 50 meters below the surface of the water. And we're going down to a depth of about 200 meters here. Picking that off here is 200 meters. And we see that during normal conditions, the water, actually we have a very shallow pool of warm water. In fact, the water is really cool. This doesn't show up very well in terms of color contrast. But you see you have this pinkish hue over here, which indicates the warm surface water. And then as we go down to a depth of about 200 meters near Australia, we have warm water. And notice that the depth of warm water decreases as we move eastward toward Peru and Ecuador. Keep in mind, we talked about high pressure. Now we're talking about the atmospheric component of it. We have high pressure, surface high pressure, and since we are in the southern hemisphere, winds around high pressure are counterclockwise. Now this is in the southern hemisphere. And so we're moving surface water away from the coast of Ecuador. And again, since we don't see a big dry hole here, obviously we're bringing cooler water up from the subsurface to the surface. And so we typically see cool waters over the eastern Pacific Ocean. Now as we begin to move along the equator and we head westward over toward Indonesia, back over toward Australia, the water temperatures, surface water temperatures, are warmer compared to the surface water temperatures here in the eastern Pacific. Also notice the depth of warm water increases as we go westward. So the surface and subsurface down to about 200 meters is warm waters. This is during a normal type of situation. Cool surface waters over the eastern Pacific, along the equator, warmer waters over the west. Now, pressure patterns, because remember we're talking about El Nino, southern oscillation, so we're talking about water temperatures. Boy, I struggle with using this. Okay. Now we're also talking about pressure patterns. And so we have high pressure over here in the eastern Pacific. We also have high pressure sitting here north of the equator. Now, since we're in the northern hemisphere, winds around high pressure are clockwise. But again, we're moving water, surface water, away from the coast just north of the equator and south of the equator. So we have the cool, cold water moving up to replace the warmer water. But, like I said, we want to talk about pressure patterns now. We've got an idea of how the water temperatures are in a normal situation, a non-El Nino condition, which is where we typically sit. Surface pressures. High pressure near Peru and Ecuador. As we go further toward the western portion of the Pacific, out over Indonesia and heading toward Australia, we have low pressure. And we know that storms are typically located near areas of low pressure, because in low pressure we have areas of rising air. And we know that air rises, it cools, it condenses, precipitation forms, and you see a thunderstorm cloud represented in this schematic here. So typically we have air rising because of surface low pressure. Surface high pressure, air sinks, and so we have clear, dry conditions over the eastern Pacific, and we have wet, stormy conditions over the western Pacific. This is in a normal type of situation. Now, notice again we have these winds flowing around high pressure, and we have typically the water begins to move from east to west. And you see some of this cooler water moving toward the west. Now, as we begin to move water here toward the west, we begin to raise the sea levels here in the western portion of the U.S. In the western portion of the equatorial Pacific, and water levels begin to decrease here in the east. And it's caused by the surface high pressure moving the ocean water from east to west. So there's a lot of information on this particular slide. You may want to pause your presentation right here, because on an exam I may ask you to describe the water temperature patterns and air pressure patterns during a non-El Nino condition, during a normal condition. So now what you're looking at is what we call normal ocean temperatures, and there's a lot of things going on here. But what you see here in this particular graph, you see 0 degrees. This is the equator. 5 degrees north, 10 degrees north, 5 degrees south latitude, 10 degrees south latitude. And so if we're thinking about this, keep in mind we have Peru sitting over here, and we have Australia sitting on this side. So again, we're just looking at the water temperatures from Peru to Australia, and we see these water temperatures, they are in degrees Celsius, and so we have 24 degrees Celsius. Let's see if we convert that to Fahrenheit. That's roughly times 2. That's about 78 degrees Fahrenheit. Over here we have 30 degrees Celsius. That would be 86 degrees Fahrenheit. So we have temperatures, water temperatures of 86 degrees Fahrenheit on average during a normal type of situation, and here, like I said, about 78 degrees. So under normal conditions, the eastern Pacific, the eastern equatorial Pacific, is some 8 to 9 degrees cooler than the western Pacific. Also notice these arrows. These arrows indicate surface winds. And remember, when we talked in a normal type condition, we have high pressure sitting in the northern hemisphere and southern hemisphere. Winds in the northern hemisphere are clockwise around high pressure, In the southern hemisphere, they're counterclockwise, and so the winds are moving the water slowly westward. So this is actual temperatures up here. If we look at the difference, in other words, we look at what we call temperature anomalies for the same area, 0 degrees, the equatorial region, 10 degrees north latitude, 10 degrees south. We're looking at differences in temperatures from the average. And during a non-El Nino condition, we see slightly cooler temperatures. And here's a temperature bar. This is normal. If we have a 0 degree deviation from the average, 2 degrees above average, 4 degrees above average, 6, and then -2, -4, -6. These aren't actual temperatures. These are deviations, or if you've had statistics, it's the deviation from the mean. So on average, temperatures are about a ½ degree cooler than normal over the eastern Pacific, and then we have a little bit of warmer water here, about 1 degree above normal. Doesn't really show us too much here. I would encourage you, if I can erase this again, I would encourage you to really look at this top graphic here. Okay, so we've looked at normal. Let me erase this. So we've looked at normal sea surface temperatures, pressure patterns, high pressure over the eastern equatorial Pacific, low pressure over the western equatorial Pacific during non-El Nino conditions. We have very deep, warm water over the west. We have a shallow pool of slightly warmer water, but overall the water is cooler, surface water, in the east compared to the west. We've looked at we've looked at temperatures here in the eastern equatorial Pacific, about 78. Over here in the western equatorial Pacific, near Australia, 86. And you know why you have cooler temperatures here, because of the high pressure. Moving surface winds over the oceanic surface, moving the water from east to west, and so cooler water from below begins to move toward the surface. Okay, let's look at what we would call an El Nino event. Now, what do you notice here? Well, first of all, you notice the thunderstorm activity, which was over Australia, is now near the Peru equatorial coast. And so we have low pressure, surface low pressure, in the eastern Pacific, and we have high pressure in the western equatorial Pacific. So low pressure near Peru, high pressure near Australia. We know that air sinks in high pressure, and so air is sinking. It's warming, it's moving away from the saturation vapor pressure curve. So we have clear skies. And we also have upward moving air with low pressure, cooling, condensing, producing a thunderstorm. So one thing during an El Nino, the pressure patterns switch. Let me go back here to a normal condition. During a normal condition, we have surface high pressure over Peru and Ecuador, low pressure over Indonesia and Australia. So inclement weather over the western equatorial Pacific, dry weather over the eastern equatorial Pacific. So we have a change in pressure patterns. Now we also notice there's actually a lot going on here. Let me erase this. We also notice that the ocean, the water is beginning to move from west to east. And the reason is because of high pressure here, high pressure here. And so we know that we have sinking air like this, counterclockwise air moving like this. And so now the winds are driving the ocean current to the east. And you remember all this warm water that we had at the surface? The deep warm water is now moving back toward the east. So now you notice that you have a very shallow pool of warm water over the western equatorial Pacific and a deeper pool of water over the eastern equatorial Pacific. Here's the surface of the water. We're going down below surface. And so now we have not only switched pressure patterns, we have low pressure here, high pressure here. We've also changed the depth of the warm water as it begins to move to the east. So there are several impacts to what happens when we have an El Nino event. Pressure patterns reverse, low pressure now in the east, high pressure in the west. And so during an El Nino, if you have constant high pressure sitting over Australia, Indonesia, you don't have very much rain. You begin to see drought conditions. Over Peru and Ecuador, this warm water begins to cut off nutrients. There's actually some very nutrient-rich materials deep in the ocean that some of the fish that are swimming around at the surface can no longer access. And so fish begin to die. In fact, the anchovy industry takes a huge hit during El Ninos. And so it affects the local economy there. Those of you that are interested in economics, El Nino affects that also. Now I'm going to basically stop the discussion on El Nino here for just a few minutes, and I want to talk a little bit about La Nina. Now your textbook there's a schematic of La Nina, which is the opposite of El Nino, and we'll talk a little bit about that. But what you probably should do at this point, I would recommend that you grab your textbook. In fact, I'm picking up my textbook right now as we speak, and if you turn it to, it's in chapter 7, and you turn it to page 197, and you look at figure 7.33. It's the subfigure marked as B, La Nina conditions. You notice that sea surface temperatures from equatorial Peru over to the central portion of the equatorial Pacific, you see blue, which indicates cooler than normal surface temperatures for the ocean, extending over a large portion of that area. So El Nino, which you look at the top, and the top figure there, El Nino conditions, December 1997. Subfigure A, you see above normal sea surface temperatures going from the equatorial coast of Peru, extending to about the mid portion of the Pacific, equatorial Pacific. You see red there, which indicates above normal temperatures. That's during an El Nino condition. La Nina is the opposite condition. Now, how do we get a La Nina type setup? Well, what you're looking at on the CD right now is the normal conditions, the non-El Nino conditions. And so you have very light winds. Again, high pressure. Remember, air flows from high pressure to low pressure, so the wind direction in this schematic is going from east to west. And during a normal condition, okay, we're talking about not El Nino or La Nina, you have very light surface winds moving water from east to west. During a La Nina setup, you still have high pressure here over the equatorial Pacific, but it becomes very strong, a strong high pressure. And so the winds, the surface winds, become much stronger. And these stronger surface winds will begin to move more and more water away from the equatorial Pacific. And in fact, it'll drag a lot of the surface water and move it from east to west. And so now this allows more of the cold water from subsurface to move up to the surface. And so you have a very large area. Let's see if I can erase this. You have a very large pool of cooler than normal waters. That is during a La Nina. Okay, so it looks very similar to an average setup. However, the winds around high pressure are quite a bit stronger, and so we begin to move more of the surface water away and bring up more and more cooler waters. So that's the La Nina setup. Okay, let's get back to talking about El Nino. Those tend to occur more frequently. And this, again, El Nino conditions, we talked about that. Low pressure over the eastern equatorial Pacific, high pressure over the western equatorial Pacific. Now, one of the things I talked about as the winds go from west to east, from high to low, begins to move the warmer water from Australia toward Peru. We can actually look at satellite imagery. And again, this is the area, this is 0 degrees Celsius. Let's see if I can change the color of this pen. Maybe highlight it a little better. Okay, so I'm kind of mapping out the equator here. So you've got Australia sitting here, Peru sitting over here, and notice that we have a very pool of warmer than normal waters. This is surface waters. Recall the water's emitting radiation. The warmer the water is, the more radiation it emits. And we can see as we go from time 1 to time 2, this warmer pool of water begins to move eastward. And eventually we see a large pool of warmer than normal waters at some time later over the eastern and central Pacific, and then cooler waters indicated here by blue near Australia. That's during an El Nino condition. Recall what I said here. Actually, I need to go forward one slide. If we look at this particular map, this is a map of deviation from normal. So again, we've got 0 is normal, the average temperature for the equator. And then we see the bar going more red, which indicates 4 to 5 degrees above normal. And we see the purple bar down here, -4. Well, you see a large area of very warm surface water. This is an indication of El Nino. And that pool of warmer water actually came over from the western Pacific because you had strong winds blowing from west to east. During a La Nina, again, we have stronger than normal high pressure. I'll change the pen color here. So during a La Nina, we have stronger than normal high pressure. And since it's stronger than normal, the winds are faster. stronger, and they begin to pull more and more of the surface water away from the coast of Ecuador and Peru. And so you see this nice cool tongue of surface water extending from the equatorial region of Peru over to the central portion of the Pacific. By the way, there's some nice links here, and in fact, let me just grab this link and I'll show you this animation if it's still active. I love looking at these animations. And you see the date here. This is back from 2007. It's going through. Again, you look at the equatorial Pacific. Difference from normal. The blue indicates colder surface temperature water, sea surface temperatures. Notice this pool of cooler than normal waters back in 2007 going all the way through the middle portion of the equatorial Pacific. Now, if we go back one slide, we can go ahead. I don't have the link for that one. That's okay. Okay, we'll move on. Now, at first glance, this is a very complicated graph here. There's something called the El Nino Southern Oscillation Index. And really, what it is, the El Nino portion of it, scientists look at sea surface temperatures, and the Southern Oscillation looks at air pressure. Again, El Nino Southern Oscillation is the interaction of sea surface temperatures with air pressure. Because the differences in pressure over Australia and over Peru is what drives the surface winds. The surface winds tend to drag the surface waters along with it, and replacing the sea surface waters with cooler waters from below. But there's an index that scientists use, and what they look at during what they term a warm event or an El Nino. So an El Nino is considered a warm event. They take this index and they take the pressure, the air pressure. Recall the average air pressure is right around 1,013 millibars, or for our class I've just said 1,000 millibars will be fine. They take the pressure at Tahiti and they subtract the pressure. Well, I'm trying to think where they grab the pressure. It's somewhere over near Peru. Boy, I'm just drawing a blank right now. Tahiti minus the pressure. I'll have to come back, and there's a difference in pressure. Basically, the way that you can look at this, and obviously I'm not going to hold you to this particular thing because I can't even remember it, but they take the air pressure over Australia minus the air pressure over Peru. Oh, I remember now. They use the air pressure over Darwin and the air pressure over Tahiti. And they take a difference and they graph this difference. If this difference is more than 3 millibars, again this is in terms of millibars, this is considered a very strong El Nino event. And if we think about this a second, let's just back up here. And you remember I tell you, don't ever memorize anything. You can figure out anything if you understand the concept. So during an El Nino, we have higher than normal pressure over Darwin, Australia. We have lower than normal pressure over Tahiti. And if we want a positive index, then we take the air pressure at Darwin minus the air pressure at Tahiti. And since we have higher pressure, a higher number, I'm just going to make up some pressures here. Let's say we have 1,004 millibars compared to a lower pressure, 900 and, let's make it 1,002. Then I would take the pressure at Darwin, 1,004 minus 1,002, and I come up with a 2 millibar difference. So it's a positive number. That would indicate an El Nino event. So again, pressure at Darwin minus the pressure at Tahiti. And we've seen some warm events through the years. You see at different years. I remember this 82-83 event. That's back when CNN was just first starting, and they were showing these large waves crashing into California, taking down some of the coastal homes. And that was the media really started getting into El Nino at that point. And then you see another El Nino, 86-87, 97-98. We've had a few since then. On the other hand, though, when the pressure in Australia has been less than the pressure in Tahiti, we end up with a negative number, which we term a cold event, or a La Nina, another way of looking at that. And we've had several of these events through the years. The most recent one, actually in 1988, this was the year of the big drought over the U.S. Corn yields, soybean yields were huge during this time, and in part because of a La Nina. Typically, La Ninas can produce a reduction in crop yields across the Midwest, and I'll talk a little bit about that later. Okay. Well, how can something that is going on way down here in the equatorial regions of Peru in Australia, how can something happening down here affect us way over here? Well, let me see if I can give you the nickel explanation of that. There are a lot of scientists doing a lot of research on this, but let me see if I can simplify this a bit. Let's say this is the ocean surface. When we have very warm waters, what happens? Well, we begin to have evaporation, right? So, you remember all this. We begin to increase the amount of water vapor that's present right above the sea surface, correct? So if we have warm waters, we promote evaporation. So we begin to increase the amount of water vapor in the atmosphere. Well, if we increase the amount of water vapor, now, boy, I tell you, we're going to use everything here that we've learned this semester. Remember the saturation vapor pressure curve? Vapor pressure increasing this way, temperature increasing this way. As we increase, let's pick a temperature here, and I increase the amount of vapor pressure in the air, eventually I'm going to reach the saturation vapor pressure curve. If I don't change the temperature and I increase the amount of water vapor in the air, I'll produce condensation. Now, what happens when we produce condensation? Well, we go from water vapor, to solid liquid. We have a phase change. When we go from water vapor to liquid, we release latent heat. Do you recall that? And latent heat release shows up as sensible heating. So we're transferring energy from the ocean in the form of water vapor. Then we take that water vapor and we condense it and we release heat to the atmosphere. Now, when we release heat to the atmosphere, something happens to the waves in the atmosphere. Now, let me just... Now, you may want to pause here and rewind just a little bit to listen to that explanation. But when we begin to release heat in the atmosphere, we begin to do something to atmospheric waves. Let me see if I can explain this. I'm going to pull up a map. I'm going to go to our forecasting links. Here we go. And I'm going to go to the upper air at Iowa State. And I'm just going to pull a one of these 500. Oh, that's messy. Let's back up. Let's pull this 500 millibar. Notice that here we have a trough. Remember these isohips? Trough. No ridge. These are all, here's a ridge right here. We have a ridge. We have a trough. And these are what we call waves in the atmosphere. Remember we talked about short waves, long waves? Now, again, this is 500 millibars, so this is halfway up in the atmosphere. If we begin to take water, the ocean water, and we begin to evaporate the water, we have water vapor. We keep adding water vapor to the atmosphere. It reaches condensation. We release heat. Remember, it's called sensible heating. And what will happen, all of this excess heat will begin to change to the wave pattern. It will actually affect the waves in the atmosphere. Just like if you were to go to the ocean and you were to take your hand and run it across the top of the ocean, you would cause a disturbance in that water. Or if you go to your bathtub, pause your video right now, go to your bathtub, put about 2 inches of water in there, and now take your hand. No, don't pause. I'm being a little funny here, but yeah, don't pause here. Just listen to the explanation. You take your hand and you begin to disturb the water. Well, it's the same thing in the atmosphere. If we begin to disturb these waves, they begin to become excited. And maybe this trough will change to a ridge if we provide enough heat energy. Now that's the nickel and dime explanation for this. But recall what I said earlier. Whenever we have a trough over us, that's an indication of inclement weather. In other words, stormy weather, clouds, cooler than normal temperatures. Anytime we have a ridge, we have dry conditions. You see, I'm outlining the ridge right now here. Dry conditions, warmer weather. Well, if we go back here, what will happen is that during an El Nino, when we have a change in the pressure patterns, remember we have high pressure here, low pressure here. This is Peru. This is Australia. We begin to produce, the water's warmer than normal, surface water, so we begin to produce clouds and thunderstorms. Rain. This release of latent heat release in the form of sensible heat begins to affect the wave patterns. And in fact, affects it in a way that what we see typically is a trough here and a ridge here. Actually, I've got this drawn a little incorrectly. See if I can erase this. So we see a big trough here and then a ridge over here. So we typically will have inclement weather down here in the trough. Here we'll have a ridge up here, and we'll see warmer, drier air with a ridge. So what happens at the surface, at the water, the evaporation adds water vapor. The water vapor eventually, we add enough water vapor to the air, it reaches the saturation vapor pressure, it condenses, it releases energy, heat energy, to the atmosphere. This energy begins to excite the wave pattern in the atmosphere, just like what I'm doing right here. In a ridge, we have warm, dry conditions. In a trough, we have cool, moist conditions. Okay, what happens in an El Nino? Well, we begin to take this southern branch of the polar jet and we begin to move the wetter area up into the Pacific Northwest. So most of the moisture coming in from the Pacific ends up going into the Northwest instead of the southern states. Again, I'll look back here. During an El Nino event, typically we're bringing in the jet stream along the southern U.S., and so we begin to bring in this warm, moist air into the southern U.S. We begin to get rain, and so with all the cloud cover, we begin to have cooler temperatures here in the southern U.S. And in fact, the southern U.S. is where we see the best effects of El Nino. So during an El Nino year, when you find yourself in an El Nino year, look down along the Gulf Coast states and you will see wetter, stormier conditions and temperatures below normal. Whereas up in our region, up here in Iowa, during the winter, and again, these are winter impacts. This is not during the summer. El Nino is very strong, has very strong impacts over different portions of the world, especially up in our area during the winter time. So during an El Nino, we'll see warmer than normal temperatures, and you'll see a dry pocket here. It looks like right around the Ohio Valley area. During a La Nina, the Pacific branch of the jet stream, instead of going into the southern U.S., begins to move up toward the Pacific Northwest. So we see rainy conditions along the western coast of the U.S., colder than normal temperatures in this region during a La Nina. And if you're sitting down in the Gulf Coast states, La Nina is pretty nice because you'll see dry, warm conditions. And the Ohio Valley shows a little bit of a wetter than normal area here. So stronger high pressure begins to move storm systems up and around the high pressure, and we begin to bring in stormy systems into the Pacific. So let's take a look at global impacts of El Nino. You know, it just doesn't affect what we have here, it's global. During an El Nino, you will see dry conditions, dry, warm conditions from November to May over Australia, September to March also over Australia. You will see wet conditions in the central equatorial Pacific over Japan from November to March. Here's the legend I'm looking at: warm, wet, and dry. Warmer than normal conditions up over Alaska and portions of Canada from December to March. Conditions are warmer than normal. I'm not going to ask you to memorize all of this. I think it would be a good idea to know the effects over the U.S. Recall that we have wet conditions along the Gulf Coast area during an El Nino. and typically drier conditions, warm, dry conditions up over the Canadian provinces. But you see, look at Africa here. Very dry conditions. So it truly is a global event. Okay, so you should have a pretty decent idea of how El Nino works. Now we're going to move from the equatorial region down here, and notice we have above normal sea surface temperatures here, almost a full degree above normal over the central and eastern equatorial Pacific, cooler than normal water over Australia. This would be an indication of an El Nino. But now we're going to leave this region. We're going to move further north, and we're going to look at something called the Pacific Decadal Oscillation. And in fact, what we're going to do, we're going to look at sea surface temperatures from Washington State up through Alaska. So we're looking at the sea surface temperatures in this area. And you notice above normal, here in red, sea surface temperatures, and then we're going to go across the northern Pacific, and we see below normal temperatures over this region. This is what we call a warm or positive phase of the Pacific Decadal Oscillation, PDO. I have it up here. So you will be responsible for understanding that for the Pacific Decadal Oscillation, a warm positive phase is when we have sea surface temperatures above normal from Washington State up through the Alaskan coast up here. And then we have north central Pacific all the way over toward Japan, a lobe of cooler than normal waters. Well, why do we care about this? Well, when we have this type of situation, there's a low pressure center. When we're in the positive phase of the Pacific Decadal Oscillation, we have stronger lower pressure over Alaska. And so what happens is we begin to drive strong storms up into Alaska, California, and we begin to create this type of wave pattern. So notice that we have a ridge here, and so we have warmer than normal temperatures over the Pacific Northwest during the winter. And since we're still in a ridge over the Great Lakes, we're going to be above normal. However, in the Gulf Coast states, we have a trough, and so we begin to see cooler and wetter over the southeastern portion of the U.S. So again, these are just waves in the atmosphere. Strong Aleutian low creates a ridge over the western portion of the U.S., over the Great Lakes, and then a trough over the southern states. Stormy weather in troughs, dry, warmer weather in ridges, and then cooler, wetter weather in troughs. Now, when I talk about Pacific Decadal Oscillation, oscillation means a change, decade means 10 years. So while El Niños may transition into a La Niña or into a neutral or normal state every 2 to 7 years, this area up here of cooler than normal water over the western portion of the northern Pacific through the central portions of the northern Pacific and above normal water temperatures, sea surface temperatures from Alaska to Washington can last on average up to 10 years. In other words, the pattern of the sea surface temperatures do not change very rapidly compared to El Nino type conditions. Now, this type of situation, like I said, is the warm positive phase. You wait a decade, it changes to something called the cool or negative phase. Now the waters from Washington State up through Alaska are in blue here, so they're below normal. So we have cooler than normal waters along the coast from Washington up through Alaska, and you see a huge area from Japan, China, all the way through the north central Pacific of warmer than normal waters. Now, in this type of situation, if we look at winters, they're cooler and wetter than average. So what ends up happening is the Aleutian low, the low pressure center here, weakens, and so we don't have such strong ridging until we get over the southern U.S. So we've got a trough here, trough over the Pacific Northwest, ridging over the southern U.S. So we have cooler, wetter conditions over the Northwest, and where we have this ridge, we typically have warmer and drier conditions in the southern U.S. Now, what's kind of interesting about all this, when I was studying for my PhD, you have to write what they call a dissertation, which is basically a long paper with original research. I always had an interest in El Nino, and since I was in ag meteorology, I had an interest in how crops were affected by El Nino. However, there's been a lot of research done on crop effects and El Nino, and so to make my research original, I looked at a combination of El Nino. So when we have El Nino occurring, in other words, warmer waters over the eastern and central Pacific equatorial regions, and when we were in the positive phase of the Pacific Decadal Oscillation, which is warmer than normal sea surface temperatures from Washington State to Alaska, I thought, let me combine these two areas. Let me combine what's happening here in the northern Pacific with what's happening here in the equatorial Pacific. Then I took the opposite case. I looked at La Nina conditions, cooler than normal equatorial waters, and then cooler than normal coastal waters from Washington up to Alaska. So for this, I looked at the negative phase of PDO. So I looked at those decades, that had the negative PDO plus La Nina conditions. Okay, negative PDO, so cooler. So what I'm looking at is cooler than normal waters up over the coast from Washington to Alaska, and then looked at cooler than normal waters over the equatorial Pacific, which was La Nina. And then I compared them with the positive phase, where I had positive PDO plus El Nino. You see here. And so what I basically wanted to see was what effect would these two mechanisms in the atmosphere, El Nino and the positive phase, negative PDO plus La Nina, and how it affected our summertime crops of corn yields. I also looked at the other two possibilities of having a negative PDO, but instead of La Nina, look at El Nino. And then I looked at the other phase of positive PDO plus La Nina. But the two big factors, well, I'll tell you, instead of talking about it, let me just show you the results. So basically what I looked at is one of the things that I tried to figure out, why do we even care about looking at El Nino, La Nina, and PDO? Well, I had an idea that these two factors in the atmosphere influenced summertime crop yields. So I knew that basically it changed the wave patterns in the atmosphere, but I looked at a couple of weather parameters. I looked at temperature advection at 850 millibars. I looked to see if it would affect warm air advection, cold air advection. I also looked to see if we had convergence of air in the lower atmosphere. Recall that when we have convergence, let me just draw the surface here, and if we have converging air meeting, it moves upward. So if we have strong convergence, we have warm air advection, that would tend to support precipitation. I also looked at how much air we're moving out of the column, top of the column of the atmosphere, looking at divergence. Recall, if I'm taking more air out of the top than I'm bringing in, surface pressures will begin to lower. Create low pressure, you create storminess. I also looked at specific humidity. I wanted to find out if we had differences in moisture in these different phases. And then I also looked at the jet stream level, the 200 millibar total wind. So in this first one, where we have El Nino and we have the warm phase, that's one connection I looked at. And then I looked at La Nina occurring when we would have these cooler than normal temperatures. So La Nina associated with the cool phase. Well, we typically, if we just look at El Nino alone during the summer, there's not a huge effect. Recall all of the other types of effects that we looked at earlier were during the winter time. Well, if you look at El Nino during the summer, you see a little bit of wet weather, it looks like over Utah, but that's the only effect in the U.S. Everything else, there's no effect from El Nino. You see drought conditions over Australia and Indonesia, drought conditions over Central America and the northern portion of South America. You have drought conditions over in India. And so there's some effects, but over the U.S. there's not a whole lot. So if I'm just looking at El Nino and how it affects summer crops, there's not going to be a lot to look at. Well, what we did here, and this looks a bit complicated, but we took the years from 1900 all the way up through 1993, and we looked at corn yields. This is bushels per acre of corn, and it's kind of difficult to see, but there are actually three lines here: a yellow line, a purple line, and then what looks like kind of a greenish line. And then you see this up and down. This is actually the raw data. So if you look back here in 1900, it looked like there was about 42, 43 bushels of corn yield across Iowa on average, bushels per acre. And if we look down here at about 1935, during the Dust Bowl era, you see that bushels per acre across Iowa was about 19. And so this is the raw data. But what Carlson et al. Tried to do with this, Dick Carlson, who is a retired professor from Iowa State, he was my major professor, he had done some research where he took an average, a running average, and ran it right through the data. And then he took a 10% above yield, which is indicated by the yellow. So he took the average and indicated 10% above that. And then he looked at 10% below the mean, which is indicated by this bluish green line that I'm trying to outline here. And what he found is that years that had El Nino, like right here, 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 and so on, were all years where corn yields, bushels per acre, were above 10% mean. Notice that all these peaks are above the 10% above mean line that he's actually drawn in here. Conversely, during La Nina years, like here, here, typically corn yields were about 10% below what Iowa averages over the years. So El Nino, above average corn yields, La Nina, below average corn yields. Well, think about this. Corn needs precipitation at times during the right time. It also needs summers that are mild. You do need some warm portions of the summer to help the growth of corn, but during La Nina conditions, you typically have very warm, dry conditions, and so the subsoil moisture that the corn roots tap into is somewhat limited, and so there's not a lot of moisture for the corn to be able to do what it needs to do to mature. Conversely, in El Nino years, you typically have above normal precipitation, cooler summers, which do not stress the corn crop as much as during a La Nina. So he found that typically there was some good relationship between corn yields and El Nino years. Well, what I did is I said, what if we add in the effects of the Pacific Decadal Oscillation and take a look at corn yields? So the positive phase, above normal temperatures, above the equatorial, from Washington to Alaska, and above normal temperatures in the equatorial Pacific, indication of an El Nino. And so what I found is I looked at Iowa and I divided it up into different districts. Northwest Iowa is District 1, North Central 2, and so on. And then I started looking at precipitation in inches over the different state divisions. So we're sitting here in Division 5, and so I looked at a situation where this red bar is indicative of a positive phase or a warm phase of the Pacific Decadal Oscillation and an El Nino event. And typically what I found is that I had precipitation higher than during a negative phase of the Pacific Decadal Oscillation. So whenever we had warmer than above normal water temperatures from Washington to Alaska, coupled with an El Nino event, we had above normal precipitation. And so then I started looking at, okay, if we have above normal precipitation, what is causing that above normal precipitation? How is El Nino and the warm phase of the PDO causing more precipitation? Well, we know from what we've learned this semester, to produce precipitation, you have to have sufficient moisture, that's number one, and then you have to have a way to lift that moist air. Remember we talked about mountain sim, moving air up a mountain, or a low pressure, stronger low pressure creates stronger convergence at the surface, the air moves up. So I began to look also at warm air advection, because warm air is less, it's more buoyant, it's less dense, and so if we're bringing in warmer air at lower levels, the air will want to rise. And what I found is a bullseye of warm air advection occurring over Oklahoma, Kansas, and portions of northern Texas. So we had warm air advection down to our southwest at 850 millibars, And then I saw that we had a large area of converging air over portions of Iowa, Nebraska, and Kansas. And that makes sense. So we have warm air in this area. We have stronger convergence, air converging at the surface, rising. So we have lifting mechanisms in place. We have warm air advection just off to our southwest. We have converging air just off to our west. And so it appears that we have the lifting mechanism available during El Nino and the warm phase of the PDO. The next question is, do we have sufficient moisture? I'm going to skip over this divergence. Actually, I won't. I'll just talk about this just a moment. This is that column of air that I've been talking about all semester. If we're taking more air out of the top, we're removing more of the air molecules out of the top, then we're bringing in at the bottom, then pressures at the surface will begin to drop. Stronger low pressure leads to more converging air. And what I found at the jet stream level, at this level up here, 200 millibars, we had strong divergence over our region, strong divergence off to the southwest. So all the lifting mechanisms at all levels of the atmosphere are in place. So the only thing left is, do we have sufficient moisture? And look at this. I looked at dew points, and I looked at the differences in dew points, and I found that I had stronger values of moisture back over Nebraska, Colorado, and portions of Kansas. So all in this area, I have the lifting mechanisms present, the strong moisture values present to produce above normal precipitation during an El Nino and the warm phase of the PDO. So I've got the atmospheric connections to produce the excess rain. So then I started looking at crop yields. And I looked at average crop yields here. This is in percent. So this means crop yields are 5% above normal, 10% above normal, 15% above normal. This is 5% below normal, 10% below normal, 15%, and 0 is what we consider normal. No deviation from the average. So what we're looking at here, we're looking at states. Here's a bar of Illinois. The green here is Indiana. Iowa is right here. Kansas is the crosshatch. So during an El Nino and a warm phase of the PDO, we find that crop yields for Iowa on average tend to be about 7.5% above normal. Why is that? Because of sufficient moisture, because of strengthening low pressure at the surface, we're taking more air out of the top, because of enhanced conversion at lower levels of the atmosphere, and because of warm air advection just off to our southwest. So it makes sense that during an El Nino warm phase of the PDO, crop yields are going to be higher than the average. And in fact, it looks like Illinois is almost 10% above average. Now, if I look at the opposite phase, which would be a La Nina and a cold PDO, look at all the crop yields across the Midwest. They're all below average. And in fact, it looks like here the winner, or I guess loser, in this case would be Michigan, with almost 7% below average corn yield. When you begin to mix La Nina with warm PDO, you have typically below average. When you have El Nino and cold PDO, you have one below, which is Kansas, and a few above. But I'm mainly concentrated on these two here. because you had above corn yields during this phase, below corn yields when you were in this phase here. So it was really interesting to see how our corn yields were affected based upon the phase of El Nino and PDO. Now I'm just going to show you a few items where I looked at El Nino during the warm PDO for code 1. I did some statistical analysis, and basically what we're looking at is the median in precipitation for an El Nino warm event for State Division 1, and we found for that the median precipitation was about 4 inches. During a La Nina cold event, it was about 3.5. And so there really wasn't a huge difference between those two events, the warm event and the cold event. However, if you see here in green, divisions 2, 3, 6, and 9, I ran statistical analysis on these median precipitation and found statistically significant differences in eastern portion of Iowa for August precipitation for these different periods. And so you look, Division 2, 4.25 it looks like during an El Nino warm event PDO, and then for the La Nina cold PDO it was less than 3. So there was a statistically significant difference between precipitation in the warm event versus the cold event. If we look at 6, we see the same thing. The El Nino and the PDO warm event, precipitation about 4.25. During the La Nina and cold event, about 2.75. So it looks like when we do a statistical difference, it looks like portions of eastern Iowa in terms of August precipitation are the heavy hitters. So if you're living over in eastern Iowa and you're raising corn, and that seems to make sense too, because we saw that the greatest corn yields were over in Illinois. So it really seems like the effect is eastern Iowa and over in Illinois for August precipitation. And I thought this would be kind of interesting just to throw this in. Elwyn Taylor, who is an extension climatologist at Iowa State University, has these crop weather forecasts, and I pulled this from last year. And just some notes here. Now last year we were transitioning from an El Nino, a weak El Nino, to a weak La Nina. And in terms of the PDO, we're in the cold phase. In terms of the PDO. So the fact that we have a weak had a weak La Nina last year, along with a cold PDO, would correspond mainly somewhere between this area and this area here. But since it was so weak, we didn't see a reduction in corn yields. And in fact, he says right here there was a 50-50 chance. Corn yields for 2007 was about 152 bushels per acre. He said the chance of record high yield was about 27%. Chance of drought was about 23%. And so everything was about 50-50 in this. So in fact, he talks about El Nino shifting to a neutral or normal condition. And so this particular crop report, with what was happening last year, didn't fit in with what we were doing in terms of our research, but I thought it was kind of interesting. And if you have some time, you might just go through and look at this particular Linzo forecast. If you go to this particular link here, you can get a forecast for whether we're heading into an El Nino or a La Nina situation. Well, I know there's a lot involved with this, but I hope that you have enjoyed this module on El Nino, La Nina, and the Pacific Decadal Oscillation. Have a good day, or evening if you're watching this in the evening.